this video, we're going to look at techniques for computing limits. There's 3 techniques that we'll use frequently, not that these are the only ways that we compute limits, but 3 techniques that we'll use often are direct substitution, factoring and reducing, and multiplying by a conjugate. At the end of this video, I'm hopeful that when you see different examples of limits that you're asked to evaluate, that you'll be able to evaluate them by knowing which technique you should use. Another thing you'll need to be able to do is when you're given a limit to calculate or to evaluate, that you would be able to apply the limit laws to evaluate them. And that's another way of saying that you're really breaking this apart step by step algebraically. Now, this is not a difficult limit to evaluate, but notice that the directions don't just say evaluate. I could actually probably teach a 6th grade pre-algebra student how to evaluate this limit, because all we're going to do is use direct substitution and replace the x with a -2. But this is not a 6th grade pre-algebra problem. It's a Calculus 1 problem asking us to demonstrate the use of the limits. So in your homework, when you see a problem that says to use the limit laws to evaluate, you do want to practice showing each of those limit laws put to use. And here's the first one. The first one is going to have to do with these sums. And the limit law is the sum of a, the limit of a sum, so the limit of x squared plus 3x plus 1, the limit of a sum is simply the sum of those limits. So it's going to look like this, the first step. We'd break it into 3 addends. So do you see what we've done? All we've done is rewritten this as the sum of 3 different limits. The limit of a sum is the sum of the limits. And then next, to really break this limit down, we're going to apply another limit law, which is the power rule. So limit of a power is the power of the limit. So we could rewrite this one as and then we have the limit of a constant times a variable. And then just the limit of a constant. I think once we've done this, we're ready to go. So for this limit of x as x approaches -2, the limit of x as x approaches -2 is -2. And then the limit of 3, oh, I am sorry, I'm noticing now when I copied that, we wanted the limit of 3x as x approaches -2 is 3 times the limit of x as x approaches -2. And the limit of x as x approaches -2 is just -2. And then we have the limit of a constant. Regardless of what x is approaching, the limit of 1 is always just going to be 1. So this, what it's approaching, doesn't even matter. The limit of a constant is just that constant. So when we simplify this, we have negative 2 squared is positive 4, plus 3 times negative 2 is plus negative 6, plus 1. We have 5 minus 6, or negative 1, which is what we'd expect it to be if we had just substituted in the negative 2. We'd have negative 2 squared is 4, 4 minus 6 is negative 2, negative 2 plus 1 is negative 1. But this question asked us to use the limit laws to evaluate, so we did want to show each step. There really are not a lot of examples that you'll need to do that, but the homework will ask you to practice that just a few times at least. This next limit, we're going to always start by trying the direct substitution. But the problem, if we substitute x with a 2, we get 0 over 0. Now the 0 in the numerator up here on top isn't a problem, but a 0 in the denominator is a big problem. You can never have a 0 in the denominator. So the direct substitution doesn't work in this problem. However, we can still evaluate this limit by factoring and reducing. We're going to factor this x squared minus 4 using the difference of two squares. You get x minus 2 times x plus 2. And then you'll notice that the x minus 2 over x minus 2 reduces to 1 because x minus 2 over x minus 2 is just 1. And now what we have is the limit as x approaches 2 of x plus 2, and we can use direct substitution, replace the x with the 2, and you get 2 plus 2, or 4. So although replacing the x with 2 gives us something that's undefined, we can still find that it's the limit of this function, of this x squared minus 4 over x minus 2, as x approaches 2, the value of x squared minus 4 over x minus 2 approaches, doesn't equal, but approaches 4. So when I say that the limit as x approaches 2 is equal to 4, I'm saying that the value of this x squared minus 4 over x minus 2 is approaching 4, not equal to 4. Here's another one where we will need to factor and reduce, but I liked this example because it pushes us to remember a little bit more of that algebra to be able to factor. The numerator, oh, and this one is going to be as x is approaching 2. And if I do the direct substitution, I find right away, oh, I can't use direct substitution because we get 2 minus 2 is 0 in the denominator. So what we're going to do is factor this, and factoring this, we get 3x minus 1 times x minus 2. Now, if you're not able to factor that yet, I really want to encourage you to practice, brush up on your factoring so that you can get that in the future. And I'm happy to meet with you during office hours, or let's make an appointment and I can help you if you need a review of factoring. The bottom, the denominator, this 2 minus x, it's important to recognize that this is the same as the opposite of the reverse. 2 minus x is equivalent to the opposite of x minus 2. So I can write this all over the opposite of x minus 2. And do you see where we were going with that? When we factor that, we see this x minus 2 over x minus 2 reduces out, because x minus 2 over x minus 2 is just 1. So what are we left with? We're left with the limit as x approaches 2 of 3x minus 1 over negative 1, which is the same as the opposite of 3x minus 1. And now I can use direct substitution to get 3 times 2 is 6. 6 minus 1 is 5. So we have the opposite of 5, or negative 5. You're welcome to pause this if you have a question about it. Please don't hesitate to ask in class. Even though you're doing this at home as a video, I am still here to help you if you need my assistance. When we try to do the direct substitution here, we get 9 minus 9 is 0. So again, we can't use direct substitution, but I don't see anything that factors obviously. However, there is a technique that you might recall, which is multiplying by a conjugate. The conjugate of, let's say, a plus b, the conjugate is a minus b. So a plus b times a minus b is what we'd call a conjugate pair. And you might remember that when we multiply these, we get a squared minus b squared. So that's what we're going to use here. If we go to the conjugate of square root of x minus 3, the conjugate is going to be the square root of x plus 3. So if I multiply by 1 in the form of the conjugate over itself, that's multiplying by the square root of x plus 3 over the square root of x plus 3, we're going to be able to get rid of that radical in the top function there, and then as a result, we'll be able to factor. So let's look at what this is going to look like when we multiply square root of x minus 3 times the square root of x plus 3. We're going to get the square root of x squared, so that's x, minus 3 squared, which is 9. And in the denominator, we have our x minus 9 and the square root of x plus 3. The square root of x minus 9 is now going to reduce, because that's just 1, and we're left with the limit as x approaches 9 of 1 over the square root of x plus 3. And now we're able to use direct substitution. And the square root of 9 is 3, so we just have 1 over 3 plus 3, or simplified, we get 1 over 6, and that's it for using a conjugate. Let's look at another example. In this example, we've got the limit of x squared minus 2x minus 3 over x minus 3 as x approaches negative 1. And you might be tempted to go all out factoring this, but let me encourage you that the first step should be looking to see if I can use direct substitution. If I replace the x with a negative 1, notice that we don't get any problem in that denominator. There's no problem with letting x equal negative 1. So I'm going to go ahead and just use direct substitution. And I'm going to replace all the x's with a negative 1. And that's all you need to do for this example. Negative 1 squared is 1. Negative 2 times 1 is plus 2 minus 3. All over negative 1 minus 3. So we get a 0 in the numerator. And please make a note to yourself that having a 0 in the numerator is okay. There's no problem with a 0 in the numerator in the top. A 0 over negative 4 is just 0. So what happened here, you could have factored this and reduced. You would have still gotten the same answer. But the easiest approach is to try the direct substitution. Or in other words, replace everything with that negative 1. Let's look at another example, an example using the Squeeze Theorem. Now, you've already looked at the Squeeze Theorem in your reading and hopefully written this theorem down, but I did want to take just a short moment in our video to talk through it. Here's what the Squeeze Theorem is saying, that if we've got this pink function and this teal-colored function, squeezing in the black function, so this black function is in between at some value, so at A, they're equal. Then we've got the pink and the teal squeezing it in. Then the limit, if there's some point where they're equal, if the limit of the pink function is equal to the limit of this teal function at some point, then it would follow that the limit of our black function, our g function, is equal to that same value, that same L. So here's how you would apply that. We're going to use the Squeeze Theorem to do an example like this. Show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. We can't just use direct substitution because we get a 1 over 0, which is undefined, but we can use the Squeeze Theorem. So let's look at how we could use the Squeeze Theorem to show this example. The first thing we want to do is just look at this sine of 1 over x. Do you remember from your trigonometry that the sine always stays bounded between negative 1 and 1? If we looked at the graph of sine, remember it looks like this. Remember that it's always going to stay between negative 1 and 1. So we can start by stating that the sine of 1 over x is between negative 1 and 1. And we could multiply everything by x squared, because x squared is always going to be positive. Let me, off to the side here, we'll state y. The range of sine is negative 1 to 1. So sine of 1 over x always falls in this range. Because x squared is greater than or equal to 0, it's not negative, I can multiply each piece by x squared so I'm going to insert in here times x squared so this inequality still holds. Why does this hold? Because I know x squared is not negative. And then what I can do next is, what do we know about the limit of x squared? As x approaches 0. I know that the limit of x squared as x approaches 0 is 0. And what do I know about the limit of the opposite of x squared? As x is approaching 0. I know that that's also, if I direct substitution, replace the x with a 0, I get a 0. And the reason here for both of these I could state is by direct substitution. By direct substitution, I've got that the limit of x squared as x approaches 0 is 0. And by direct substitution, I have that the limit of the opposite of x squared as x approaches 0 is also 0. Well, we've got our squeeze. We've got the pink function has a limit that's equal to the aqua-colored function. So the limit, this x squared on the outside and the opposite of x squared on this other side both have a limit of 0. So what do I know about the limit of x squared times sine of 1 over x as x is approaching 0? I know that this limit has to be the same as the limit we got here, because these were the same, and because our x squared times sine of 1 over x is squeezed in between these two, I know that its limit must also be 0. So the reason I'm going to state here is going to be by the squeeze theorem. By the squeeze theorem. And that's it. That's just an example of how we could use this squeeze theorem to help us with some limits. If you have questions, I hope you'll either bring your question to class, send me an email. Best would be if you sent me an email and then I could bring it to class for you, or post your question on the discussion board. But thanks for watching the video. I hope that you are able to understand some of these examples. You might be able to jump in and start the homework even before we get to class, where we'll be able to practice this.